All right, today we're going to do something pretty cool. We're going to decode the hidden signals, the secret language really, that's buzzing inside our most critical industrial machines. We're going to learn how to listen in on a machine's vibrations to actually predict failures before they even happen. And we'll be focusing specifically on how to calculate those all-important bearing fault frequencies using some industry-standard formulas.
So really, how do you listen to a machine's heartbeat? I mean, think about it. In a way, that is exactly what we're doing. Every single rotating machine out there, something like the Morgan NTM mill from our source material, it's constantly communicating its health and, its distress, all through vibrations. Our job, our mission, is to translate those vibrations into a language that we can actually understand.
Okay, so here's our game plan. First, we're going to really understand the challenge we're up against. Then, we'll dive in and decode the 4 key fault frequencies you need to know. After that, we'll cover some absolutely brilliant rules of thumb for quick diagnostics out in the field. Then we'll get real and explore why the real world is always a bit more complex than a perfect formula. And finally, we'll wrap it all up by showing you how to turn all this data into a clear, confident diagnosis.
All right, let's jump right into Section 1, a machine's hidden language. You really can't overstate how high the stakes are when we're talking about heavy machinery. An unexpected bearing failure, that can lead to absolutely catastrophic downtime. So identifying these issues before they become critical, that's the entire game.
And this right here, this gets to the very heart of the problem. Look, if a fault vibrated at the exact same speed as the machine's rotation, well, that'd be easy to spot, right? But the tricky part is, most bearing faults are asynchronous. What does that mean? It means they create their own unique frequencies, basically hiding in all the other noise. And that is why we need a much more sophisticated way to hunt them down.
So, if these sneaky faults are hiding, how in the world do we find them? Well, that brings us right to our second section. Here, we're going to decode the fundamental language of bearing analysis. This is where we learn to translate those unique, hidden vibration signals into specific, identifiable faults.
Now, the good news is we are not going into this blind. We have some really powerful tools at our disposal. You've got formulas from industry leaders like CSI and Charlotte. These are the trusted standards, the go-tos. They give us a super reliable mathematical basis for figuring out exactly what frequency to look for when a specific part of a bearing starts to go.
Okay, so let's break these down. The first key frequency is BPFO, which stands for ball pass frequency of the outer race, and it's pretty much exactly what it sounds like. It's the frequency you get each time a single ball or roller passes over a defect, a tiny little flaw, on the stationary outer race of the bearing.
Up next, we have BPFI, the ball pass frequency of the inner race. You can totally think of this as BPFO's sibling, but this time we're talking about a defect on the inner ring, the part that's actually rotating with the shaft. And because that part is moving, the frequency is going to be different. And yeah, it's typically a bit higher than BPFO.
Then there's FTF, or the fundamental train frequency. This one's all about the speed of the cage. That's the component that literally holds all the balls or rollers in their place. And listen, a problem with the cage can lead to a really catastrophic failure. So this frequency, this is our critical early warning system.
And rounding out our big 4, we have BSF, or ball spin frequency. This is just what it sounds like, the frequency of a single ball or roller spinning on its own axes. If you've got a defect on one of those rolling elements itself, this is the signal it's going to send out. So there you have it, BPFO, BPFI, FTF, and BSF. These 4 frequencies are the key signals we are hunting for.
Okay, so now let's get practical. Knowing all the theory is great, but when you're out in the field, you need a fast way to check if what you're seeing actually makes any sense, right? Well, this next section is all about that. We've got some fantastic shortcuts coming up.
And this insight, which comes from an industry contributor named Dave, is just pure gold. Seriously. He shares some general multipliers that are a total game changer. So instead of having to run a complex formula right off the bat, you can use these to get a really quick idea of where in the vibration spectrum you should even be looking for trouble.
So let's say you see a mysterious vibration peak pop up at, about 4 times the machine's running speed. Well, this rule of thumb immediately tells you, go investigate the outer race, the BPFO. What if you see something hovering around 7 times the running speed? Bam! Your prime suspect is now the inner race, or BPFI. It's just such a powerful diagnostic starting point. And check this out. Dave gives us another amazing verification technique. He says to add your BPFO and your BPFI multipliers together. That sum, it should be equal to the number of balls or rollers in the bearing. So, for example, if your BPFO multiplier is around 3.5x and your BPFI is 5.5x, well, they add up to 9. That strongly suggests you're dealing with a 9-ball bearing. It is just a brilliant little cross-check to have in your back pocket.
Okay, so those formulas and rules of thumb are absolutely essential, right? But, and this is a big but, they're not the whole story, not even close. So in Section 4, we're going to explore why a truly professional diagnosis means accounting for all the messiness of the real world.
Now, to be perfectly clear, the source material absolutely confirms that those formulas from places like CSI and Charlotte are highly reliable. I mean, they are the bedrock of modern vibration analysis. But, as contributor Joshua Thomas points out so well, the real world is always more complicated. And here's the crucial point to remember. That calculated frequency you get from a formula, that's a theoretical value. Real-world conditions, things like load and temperature, they can and they absolutely will shift that frequency, even if just slightly. And check this out. Vibration expert Dr. Howard Penrose gives us this brilliant roadmap of how a failure actually progresses over time. See, it's not like a switch that just flips. A failure doesn't just appear as a single perfect peak. It usually starts as some high-frequency noise or metal-to-metal contact. Then the classic fault frequencies start to emerge. After that, you'll see a rising noise floor around those frequencies. This 4-stage model is just critical for understanding how far along a failure really is.
So, okay, what are these real-world factors we need to worry about? Well, this basically consolidates warnings from a bunch of different experts. For instance, a really heavy load can physically deflect the bearing, right? That changes the roller contact angle just a bit and boom, it shifts the frequency. Or think about poor lubrication. That increases friction and heat, which is also going to alter the vibration signature. And then there are technical issues you have to watch out for, like having insufficient resolution in your data. That could make a real fault look like something else entirely. It's a lot to consider.
So with all of this complexity, you might be asking, how do we ever get to an accurate diagnosis? Fair question. Well, our final section is all about that. We're going to pull everything we've talked about together into a set of clear, actionable best practices.
Really, the key takeaway here is this. It's about building a case, like a detective, not just finding a single number. You can't just rely on one calculation. You have to correlate your data with the actual physical conditions of the machine. If you can, get data directly from the bearing manufacturer. That's a huge help. And always compare your readings to the machine's own history. Is this vibration new? And finally, use industry standards like ISO 15243 to help classify exactly what kind of failure mode you're seeing. And that brings us to our final thought for today. The formulas, the data, the rules of thumb. They give you the what, the where, and the when. But the real skill, the art of being a great diagnostician, is understanding the why. So the question I'll leave you with is this. Now that you have the data, what is the machine really telling you about its condition, and what does it actually need? That is the ultimate question.